Right, problem 2.5. So this system has a collar which has a mass of 14 kilograms, and it's connected via a spring to this point here, and it's also connected via this cord over this pulley to this weight B here. So as A moves to the right, B goes down. So let's start off by defining two states. So state 1 is the at rest state, so the initial state, and state 2 is once it's moved 20 centimeters to the right. Move 20 centimeters that way. And if this has moved 20 centimeters, then because they're connected, you know that the weight B has moved downwards 20 centimeters as well. So let's draw just a picture of the spring in these two states. That's going to be helpful for us later. That's how it is initially. Not a brilliant picture, is it? There we go. And that distance is in the question. It says 0.3 there. And that distance is 0.15 meters. Now once it's moved, the spring end, one of the ends of the spring moves and it extends. I haven't drawn that nicely, have I? So that distance is the same, it's still 0.15 meters, but this distance, although it doesn't look like it from my drawing, has actually extended. So this is the original position, and it's moved an extra 0.2 meters. So hopefully that's clear. And yeah, as I say, we'll use that in a bit. So in this system, there are only conservative forces, the spring force and gravitational force. So that means we can look at lecture 2 and use our expression for potential energy plus kinetic energy as constant and evaluate that at the two states. So the potential energy plus the kinetic energy at state 1 is equal to the potential energy plus the kinetic energy at state 2. Simple. So what we're going to do is evaluate each of these terms, and we're going to eventually find out what the kinetic energy at state 2 is, and that will tell us what the speed at state 2 is. Now, to begin with, it's at rest, so we can straight away say that the kinetic energy of the system is 0. But also we can define the datum points for each of the two masses as being the positions of those masses in state 1. So in other words, we can define the elevations of each of them as being 0 in both cases. So the potential energy of the masses is 0 in state 1 too. And also from the question, it says the system is released from rest with the spring unstretched. So that means that there's no stretch in the spring, so there's no stored energy in the spring either. So potential energy at 1 of the system is 0. Now we're going to evaluate the potential energy at position 2, and well, let's work out the potential energy in the spring because it's extended, and what we're going to do now is work out how much it's extended. It's got an amount of stretch. So let's define R1 here as the length of the spring at position 1, and it's not the same as the stretch, so it's not compressed or in tension at all here, so this is unstretched at this position, but this is the length of it, and we can get that from Pythagoras. There we go. And the same in state 2. It has a different length, 0.15 squared plus, well now this is a length 0.5. So how much is the spring stretched in this position? Well, if we go, in fact, I don't think we need to go back to the lecture to remember that stretch is defined as R2 minus R1, where R1 is the unstretched length. Actually, in the lecture notes, I use R0 to define unstretched length, but that's equal to this length. So to calculate the stretch at position 2, it's just the difference in length. There's nothing really fancy going on. So let me calculate that. So the square root so this is the length at position 2 I'm calculating now, 0.15 squared plus 0.5 squared minus the length at position 1, so the unstretched length, 0.15 squared plus 0.3 squared. Okay, that is how much it's stretched when it gets to position 2, 0.1866 meters. So now we know the stretch, we can determine the potential energy in the spring from this expression, which we derived in lecture 2. So it's equal to half K S2 squared. But there's other potential energy in state 2, because in moving the collar from A to 20 centimeters to the right, the mass here, mass B, is dropped 20 centimeters. So we've also got a potential energy term due to mass B moving, and that there is the elevation of B at position 2. Do you remember I said that the elevation at position 1 is 0? So this elevation is going to be negative. So let's put values in now. So we should have half. The spring constant is 700 newtons per meter. The stretch is 0.1866, and that will be squared, plus MB, which the mass of B is 18 kilograms, times 9.81 times minus 0.2, because, as I say, it's gone down, and that equals, what does that equal? 0.5 times 700 times 0.1866 squared plus 18 times 9.81. I wouldn't advise you doing this long an expression on your calculator because you can't see it necessarily. It's a little bit harder to do. That's equal to minus 23.13 Newton meters. So we're almost there. Our expression for the kinetic energy at state 2 is equal to half ma v2 squared plus half mb v2 squared. The speeds are the same because they're connected, and that simplifies to half. Well, the two masses added together give you 18 plus 14 is 32. Yeah, of course it is. V2 squared equals 16 V2 squared. And from this equation, we can now substitute in these values. Well, that goes to 0, doesn't it? That goes to 0. And we're going with V2 equals minus T2. So 16 V2 squared is equal to minus V2, so it's equal to 23.13. V2 squared is equal to 23.13 over 16, which, well, let's just go straight to the answer. Sorry, this is little v, by the way, not capital V, so it's not, this is speed, not potential energy. 23.13 over 16, square root of that is 1.2 meters per second. And that is that. Cheers.